Okay, sorry about that. The mute button. Let me see. Jeremiah has been jumping up and down literally for about half an hour. So,
Okay.
Jeremiah, let me let you go first, sir.
I've been really excited about what Gary's presenting here. He's talking about how the space-time curl can effectively pinch or squeeze the gravity wave, and it produces photons that we can detect. I mean, that's incredible. The linking between an electromagnetic field or just a fixed magnetic field and an incoming gravity wave that traverses through that field, and the idea that it produces a signal that we can then detect, it really draws a solid link between electromagnetism and gravity, which is, of course, that big unifying factor that we've all been searching for, that physics has been dreaming of fixing forever. So this gives us a really functional way to look for if our devices are actually producing any kind of gravitational waves, because it's a mechanism. And it's very simple in your setup. You just have a really strong field. So one of my big questions for you, Gary, was in your system, you use a 9 Tesla field, an incredibly strong field. And I'm guessing that's just to get your noise floor low enough to the point where you can detect?
Yeah, it's a function of the magnetic field strength. It's a function of the sense beam strength. And so the weaker the signal, the higher the B field has to be. So you can imagine if your signal's not 10 to the minus 32, but 10 to the minus 20, now you can divide that magnetic field by that many orders of magnitude and get the same effect. So it really does scale that way.
That's incredible.
Another issue I was thinking, with 9 Tesla and you're dealing with stainless steel, that will like destroy the vacuum chamber, wouldn't it?
Yeah, it'll warp your vacuum chamber. Yeah, so you really have to be careful. What are you going to make your vacuum chamber out of? And it may be composites.
I mean, I don't know about titanium, might be a better choice. We do have a stainless steel vacuum chamber over here. We do have superconductors and 10 gigahertz signal generators. We could push 20 watts with our traveling wave tube amplifier, and I think we have pretty much all the components except for that that layer that you're talking about, the
the fractal membrane. Yeah, you can design that. You can etch that on a PCB. So I don't think it's that tough. It's that tough to design. I think what you have to do is spy a little bit on the cell phone companies, because it's very proprietary, these fractal membrane designs. You can find research papers on it, and probably it's easier to find a higher frequency microwave one than it is cell phone frequencies.
I mean, PCBs are cheap to order, right, Gary? We can order a set of PCBs for basically like $20 now online. So
sure, if you have the etched pattern, you can send them to a PCB house and have them etched for you.
Yeah, that's amazing. Would you be interested in maybe working with us a little bit to try to replicate some of these things? Is that
I am not a fractal membrane expert, but I could certainly point you to some research articles I've collected over the years.
Not just on fractal membranes, Gary, but you're obviously a genius. And you
sure, yeah, we can work offline if you want me to help consult.
Yeah, I mean, we want to build based on all the stuff that's in your brain, because there's definitely a lot going on there, and you presented some really fantastic and important things that have huge implications in the experiments that we're doing right now. So
I have a few spare clock cycles every week, so I don't know how much I can help you guys, but I'd be happy to get with you offline.
Also, our investor or donor actually offered, like, if anybody has relevant information, he'll fly them out here and pay for all expenses to come down to the lab and actually work with us live on these experiments.
Yeah, that'd be fun to do once the COVID thing's over, which seems like months, not years now. So sure.
If anybody's brave enough to traverse the COVID environment, I mean, the availability to come out and help out at the lab is there. It's an open offer, basically. So
it's awesome.
Anyone's interested in helping, and especially, I mean, we want to work with you, Gary. You're brilliant. I love the information you present, and I'm very excited about it.
We rented a guest house for any visiting scientists. Jeremy and Travis were in it the other day, and we have pretty much all the components that you were talking about. We got 18.5 gauge wire.
Yeah, I love poking around labs. I'm myself, so I would love to come out and poke around sometime.
Yeah, and I was thinking of powering the 9 Tesla field using the hybrid batteries. This is primarily a hybrid battery shop. This is the back of a hybrid battery shop. So we could use those are very good at very high impulse energy. So we could probably get to 9 Tesla but I would be afraid what would happen to that, stainless steel. Or
Yeah,
any
the
area.
CAT version I saw of that detector later on looked more like a diving bell, pressure vessel than it did an ordinary vacuum chamber. So
That makes a lot of sense.
And
yeah,
it
it
probably
looks
not made
odd.
out of stainless steel. You can't make a
Well, you
stainless steel.
could. I mean, as long as you structure it and you make sure you make that. So technically, I mean, the magnetic field just needs to be present where the gravitational waves are traveling through, right? So you could
Just the
have a
core.
very tight field with a closed external loop. So
That's
it
right.
would be-
Yeah, so it's just in the sensing core itself. Yeah.
So could we then use a yoke to effectively focus it and remove the external forces on the stainless steel walls of the chamber?
Sure, potentially. Hmm.
Okay, awesome. We just need to find some really good materials to build a yoke out of then. And perhaps very, very pure iron, because if you guys have looked at the response of materials in magnetic field, very, very pure iron. The more pure you get it, even by the fraction of a percentage, actually increases the maximum saturation of that material and gives us a huge area to work with.
Would these are about 1-inch YCBOs. Would this work?
1 inch by about ½ inch thick. Probably
Yep.
not going to get any of that, hey?
I can't off the top of my head speak to that. It depends on the index of the material. But those are probably very high index. That's a very high index material, probably.
They came from the Czech Republic.
They're a bit hard to pin. We don't know for sure if they're going to work for the Pakhanov replication, because according to Porer's papers, Pakhanov had cracks in his superconductors, which caused him serious problems. And these definitely do show some signs that where they were cast, there are some cracks that may be deeper within the structure than we can investigate. So they may not, in fact, work for Pakhanov's impulse discharge, but the idea that a B cross B can warp spacetime is going to be critical for us to understand how to build this thing. There's always that bilayer mystery, and I just sent you, Tim, email this a little bit earlier about Porer's stuff and how he talks about using Josephson junctions in his superconducting emitters, and that's his big key. So that would be basically Pakhanov's bilayer to produce one large Josephson junction compared to millions of them within the structure to produce gravitational waves.
Well, so Jeremiah, let me ask around a little bit and see if anybody else has questions. It looks like so.
Thanks. Sorry.
Oh no worries, no worries. Okay. Oh, let me see. Mr. Murad has a question, sir. And I need to okay.
Can you hear me, Gary? It's good seeing you.
Yeah, likewise, Paul. Hi.
All right. Regarding MRIs, they have 1.5, 3, and 10 Teslas. So to work with 10 Teslas isn't that big a problem. The comments that you made that I'd like to, I guess, make some suggestions is that, well, the US government guys, probably no one's interested in high frequency gravity waves because they don't understand technology. And if you haven't got somebody to bless, it goes nowhere. Now, I don't know if Sal Pace will be the guy to talk to about that, but that might be an approach. And, Frank Mead is gone. Now, regarding the AIAA article, the articles itself was kind of skeptical. Never did say anything like, hey, it's an alien vehicle. We just don't know. We don't know. And I had gotten involved in about 2 weeks of arguments on AIAA Engage about UFOs. And the bottom line there was that, yeah, it's an article, but we don't believe it. And, like, bingo, none of this means anything. So you take that with a grain of salt. Regarding the Sarfatti comment, the physicist doing this normally says C is equal to 1, H is equal to 1, and so on. And everything looks great.
At all to actual units the engineers use, yeah.
But you looked at that equation, and it's 1 over C to the 4th. And to get over C to the 4th, that's a lot of power. And, I remember a conversation that Eric Davis said that you may bend the curvature of the space-time continuum with a nuclear explosion. And he's probably right. It's just tough to get to that C to the 4th.
That energy level, yeah. That's why we looked at the high frequency, right, to try to help with that situation, because then you've got the stress energy metric changing fast enough that derivative helps increase the effect.
Well, you didn't show Baker's comment about that 1 to the C to the 4th anyway in gravitational wave detection. So you have the same problem as what you're seeing with the way Perfetti's working the problem.
Yeah, it's a lot to overcome that C to the fourth.
Okay, that's all I had to say.
Okay, so let me thank you, Paul. And then let me see who else has questions. Jeremy Reese had asked, he was wondering if you could use laser etched metals instead of nanowires. And Jeremy just left. Okay, so
But potentially, yes, you can etch the wires. That is one way to make the wires. I like superconducting wires because they carry more current. More current means more electrons. More electrons cycling means more change in the stress energy tensor.
Okay, and let me see. He's in the room. I think he's just focused on something else. Let me see. And does anyone else have questions for me? Just raise your hand if you'd like, or you enter them in chat.
Jeremiah here.
Yeah, I've got
okay.
another question for Gary. What we found out from the last APEC conference from Richard Van Duyk was about the extremely high electron drift velocity in new materials like graphene nanolayer films or stacked graphene films. Could these potentially be a room temperature solution to maybe building a non-cryogenic gravity wave detector?
Yeah, potentially. The currents are a lot lower than superconductors. So I really like the high currents of superconductors, but if they can either get their the current density up, or if these nanowires can get the critical temperature up, either approach would be good. It would really be nice to get these nanowires to operate at refrigerable temperatures, so you could put it in a refrigerator instead of a dewar.
Yeah, I mean, I think right now, seeing as this is the an engineering conference, this is a challenge of engineering to figure out how to make these materials so that we can produce gravitational wave detectors and gravitational wave generators that operate at room temperatures without special cryo systems. I do think it's possible, and Van Duyk pretty much proves that he can.
And it may be. I'm not looking for the right current source. One of the reasons I use the nanowires is because the person that urged me into presenting this paper was William Riken, who is a nanowire researcher in Japan. And he had some material, he doesn't know what to do with it. It's like, it doesn't need to be this good for transformers. I mean, it's 30 nanometer wire that carries 200 amps. It's like, what is this for? I'm like, well, I can think of SMAS, number one. And number two, I can think of a forward coil.
I think every lab on this conference could probably use some of that in their lab. Yeah.
I mean, we have everything needed to put
strong magnets, right? Electromagnets.
Yeah, we could create crazy strong electromagnets over here. We have nickel batteries.
Right now, it has to be in a dewar that's 220 Kelvin at least, if not 200 Kelvin. So critical temperature, he can't really get it above 200, 220 right now. That's his limit.
That's something that I think we can actually develop and work through on the engineering side. I think we have what we need now in technology to be able to.
Thermoelectric cooling comes pretty close if you're looking at cooling tech. Yeah.
Yeah, forward stack can get down pretty low.
Once you're in a vacuum chamber, the superconductor maintains its temperature pretty well. And we actually have a mechanism to keep the superconductor cool using a
contact surface probe.
Yeah, like a contact surface probe. So once we get the superconductor at its critical temperature in its pinned form, we can put the probe in there inside the vacuum chamber and keep it cool.
The other nice thing about his material is, not to get too far off of gravity, but his material is slow quench. We don't quite know why, maybe flux spinning, but for whatever reason, it's very slow quench. So if it does reach its critical temperature, it doesn't quench instantaneously. It doesn't explode, which is nice from a safety point of view.
Hey, welcome, Richard Van Duyk.
I am so glad to see you here.
Oh, yeah, thanks. It took me a while to get over here.
I've been talking about you since you haven't been here.
So, hopefully it was something good, not bad.
It was all praise.
Oh, okay,
I'm very
thanks.
excited about replicating your experiments. Very excited.
All right,
Falcon Space
thanks.
this month is doing that.
All right. Well, I just wanted to see, what's going on now. Are you guys still in the middle of this gravity wave presentation?
We're in questions and answers at this point.
Okay.
Jeremy, how's the live stream going?
Guys, we have 120 people, 117 right now.
Are there any questions from the audience?
Yes, Gary Chase wanted to ask about the effect of HFGW to induce dipoles in the particle-antiparticle pairs in the vacuum, such as electron-positron pairs. And
yeah, it could be strong enough. It's a very weak effect, so it probably wouldn't be strong enough to do anything like that. For that, you need pretty extreme fields and situations.
Right, in order to break that Schwinger limit. What is Gary's awareness of induced dipoles in electron-positron pairs in the vacuum in response to HFGW?
Yeah, I need a black hole to do that.
Yeah. I had a question about what I wanted to ask you in relation to some of the materials about metamaterials and ways to. So the nanowires is kind of an expensive way, and I wanted to point to some research that I came across recently in Sci News, and I'll send the link in the main chat right now. And that was a team that was at University of Rochester, I believe, and they're working with laser etched metals, and they're able to create
and plasmatrons and polaritons. Okay.
Yeah, the polaritons, the surface plasmon polaritons, and they're able to create these types of metamaterials using just laser etchings on metal. They etch like a grid pattern or a lattice onto a metal, and that actually produces a metamaterial.
Nice. Well, that could be the kind of skin that we need to make a craft like this operate. So.
Yeah, this is definitely some research I'm hot on, and I just wonder how accurate this needs to be to laser etch these metals. But anyways, I was curious if you'd heard of that, because you brought that up too, and
this is brand new. The whole using these metamaterials to help affect gravity is brand new to me. I think it was mid to late September when Jack first presented that. And it was brought to my attention, and when I reviewed it, I thought he really did have something. And so I had been communicating with him off and on it. But I haven't gone into detail on exactly what metamaterials could be useful here. Until now, my only exposure to metamaterials was for like stealth technology, where you're talking about creating a negative index at radar frequencies. But to create a negative index in order to manipulate gravity, that's quite a different problem. And I think it's going to be an area of research that is going to take many years to sort out. And as I was pointing out during my talk, I would advocate for gravitics labs, perhaps at places like JPL or Applied Physics Lab, people that are used to building things. And I think that would be a really valuable thing to do. And so far, we just don't, we haven't really seen that development happen quite yet.
Okay. So does anyone else have questions for Gary? Let me see. Ron, you have looked like you might have a few. You're muted, sir. Ron, you're muted there.
Yeah, I think he's still on mute.
Okay. Yeah, he's still on mute.
I'll ask a question.
Well, what Ron is actually trying to.
Ron, have you unmuted? Just looking for the unmute. I think you have to hover over the bottom to
okay, I got it. Yeah, I think Jeremy mentioned electron-positron pairs. No?
Yeah. Why, Ron?
Yeah,
It was Gary Chase from the live chat, but yeah, I brought it up for him.
Oh, okay, because here is something from UFO. One of the most interesting books is called UFO Quest. And UFO Quest, you're familiar with UFO Quest?
No, okay. I haven't seen it.
Yeah, it was written by Alan Watts, but it's not the Alan Watts that wrote The Way of Zen. What I'm going to do is just, our fax machine at the library is broken, and so I sent this out via iPad. But I want to see if this comes across. There's the creation creation of electron-positron pairs down here.
Okay.
It's a magnetite sandwich. The top of the UFO is single crystal copper. And this was investigated by the University of Manchester back in the 50s.
Really?
And oddly enough, the University of Manchester, I'm linked in with somebody at the University of Manchester, I should know, but there are a few things that I've seen from maybe Rob Chambers will know, because are you familiar with Green Glow? The Green Glow people from BAE?
Yeah, I think they're here. Brian Evan can get off mute, and then Rob Chambers is here.
Yeah, because this was taken, this is all British. It's SILPHO, SILPHO more. And hopefully this will come in. And what they had at the top was a gamma gun that circulated. It went through a magnetite sandwich with a dielectric, a polymeric dielectric of styrene that was of such density. I think it's easy to find styrene if we all burned, not that I burned many plastic models, but it's burn and sniff. When you burn styrene, it has the odor that's characteristic. And so I guess they did a burn and sniff, and they did a density test. And they said back in the 50s, they knew of no styrene of such density. And so one thing I get involved with is benzene ring materials. And when you subject them to electric fields, you change the electrorheological properties. They shrink together. They screw up my electrodes because they go away from the electrodes into the densest field. And so you think you have a complete electret, but what happens is you have a lot of vacuous space because of the contraction. But this was done with a magnetite sandwich. It's called SILPHO more, and there's 4 pages. Amazon has it for like $8. A few people I know bought it, but in terms of just being, some of the names in here are just incredible. The British Non-Ferrous Metal Materials Association, they're the ones who's ascertained that it was a single crystal copper. And it was a dual ply laminate. Also, Department of Metallurgy at the University of Manchester, the Cavendish Laboratory at Cambridge, and the University of Manchester came to the same agreement. And it's all within here. I do have a bad copy I can email out, but the main thing is it was copper as a superconductor, double laminate, 2 laminates, a magnetite sandwich, then a bottom layer of single crystal copper. So if anybody wants it, but with Jeremy, he was concerned with the electron pair creations, and it was done through this gamma gun at the top that rotated. So I'm out. Nice meeting everybody.
Good to see you, Ron.
Thank you again, Ron. So Wayne actually had a question. Wayne, let me unmute you there.
Yeah, hi. Yeah, so I wasn't able to listen to the whole presentation without interruption, so I might have missed a few things. I was just wondering about the forward coil you were talking about. I've seen that picture before on the internet, and it was intriguing. And I was just wondering if you could comment on some of the practical design approaches that we might take in making something like that, or what.
I can certainly address the challenges. And the first challenge is that G over C to the 4th term drives the number of turns in the forward coil extremely high. So you want a really high M. If you can get 1 billion turns, great. So that is going to be a design constraint. But with high permittivity or permeability core in the middle of it, that could shrink the number of turns needed quite substantially. Second thing is if you're going to use superconductors, which I have proposed, winding the segments and then connecting the segments together also almost has to be, because the number of windings almost has to be robotic. So you need a machine to do the windings. Now, there are machines designed to do motor windings. That's how we get very inexpensive electric motors. we would need to use and adapt some of those machines that do motor windings to doing these nanowire windings, only at a much different scale. So the scale of the nanowires is much smaller. The packaging of the nanowires and the connecting of the nanowires is problematic because you might be able to get current into a nanowire, but how do you connect it to other nanowires? That's been worked out for fiber optics. It's not been worked out for nanowires.
Okay.
One of the approaches to nanowires that William Ryken suggested to me was embed it in fiber optics, and then you can use fiber optic connectors to center the device. You still have the problem, even when you're bringing those two fiber optic pieces together with the superconductor itself. How do you make sure they punch together tight enough that you maintain superconductivity between two carbon nanowires? One of the reasons it's a superconductor is it's a crystalline structure. These nano wires are essentially aligned nanorods. So getting those nanorods to couple to other nanorods in a favorable way. The thing that works for you is they are slightly magnetic. You don't think of carbon as a magnetic material, but carbon nanowires made out of carbon nanorods are highly magnetic because of the alignment of the domains. So that might actually help you a little bit on getting these things connected when you try to start connecting these different segments together. So
that sounds like some advanced material engineering.
Yeah, you're gonna need some serious material engineers on this. As my co-authors, Marcel Grossman, were both material engineers. I was the only physicist, system engineer. The other two co-authors were material engineers.
So my interpretation of that, when I saw the diagram, my interpretation was that what was going through those coils was not electric current, but mass flow. So maybe a fluid or something that was
right. And my point is you're treating the electrons as mass flow. It's the mass of the electrons that are important, not the charge.
Right.
For electromagnetic effects and SMS devices, you want that charge circulating, the charged electron. For a gravitomagnetic coil, you want the mass of the electron. So here's another way to increase it would be push the electrons until they're relativistic. And so if you, and I have a table in my Marcel Grossman talk that shows the impact of different betas and gammas of different relativistic speeds of the electron. And the electron, with respect to the rest frame, which is where we want the gravitational effect to happen, if you push those electrons into a relativistic mode, they weigh more in the rest frame. And as soon as their mass goes up, you get more effect. Now, the problem with that becomes energy leakage, such as shrink-off radiation, as you get with any particle accelerator. So what you wind up having on your hands is a donut-shaped particle accelerator now. And so all of a sudden, with shrink-off radiation, you have all of the problems attendant with particle accelerators. So
is that related to the synchrotron radiation with the electrons accelerating?
Electrons accelerating through a medium, in this case, a nanorod medium, are going to emit shrink-off radiation. So you're going to see that as an energy drain, as well as you might start ionizing air. This might start glowing blue.
Yeah.
Okay.
There's been a lot of talk about rotating mercury in some of these discussions. Mercury being very dense.
Yeah.
But there's other dense.
Yeah, mercury vapor. Another idea that's been tossed around that I actually disclosed to United Technologies was using liquid helium. It's a superfluid. Because superfluid, it has very low to no friction, as long as it's maintaining a temperature where it maintains its superfluidity. You can also ionize it with ionizing radiation to the point where you can use electromagnetic fields to accelerate the superfluid and manipulate the superfluid using pinch fields. I can't remember the name of the pumping. It's a kind of pumping where you're So the diastolic pumps.
Peristaltic.
Peristaltic pumps. So you can use a peristaltic pitch field to push the liquid helium through a tube, through these tubes, and accelerate it to extremely high rates. Ionized helium nuclei have a much greater mass than electrons, thus a bigger effect. The problem you wind up with there is it's gonna be radiating because you're ionizing, so it's somewhat radioactive. So you have to have it in a chamber just for radiation, but it's a very weak radiation, but it will be somewhat radioactive, the test setup, simply because it has to be to ionize the liquid helium. So that's going to be a constraint.
Also a constraint is
Liquid Technologies took a pass on that patent. So I said, do you mind releasing your interest in it? And they're like, no, we're just gonna keep it for now. So they chose to not patent it and not release it. So less for anybody who discloses patents to companies.
One more little question. With the fluid, whatever this fluid or these particles be, would they have to be in like it would be a constant current or a pulsed type of current?
Well, the nice thing about a toroid is it might look like a constant flow, but the direction is always changing. So the energy tensor is changing. So the stress energy has a derivative even in a constant flow.
Okay.
You only need the change in flow if you're trying to do AC, if you're trying to do gravity waves, then you need a changing flow. But just to do scalar gravity, you can do it with the constant flow.
Okay, so let me go to, actually before Mark jumps in, let me jump to Franklin, who has been patiently waiting with a question for a while. Sir?
Hey, Gary. Yeah, I've never really heard of this high frequency gravity waves, and I wasn't really sure why anyone would be interested in them. But just to try to clarify where you're at with your research. So it looks like you're proposing that these things can be detected, but you haven't actually built anything that has done a detection. Is that where you're at?
That's right. Yeah, that's right. I'm not building any of these. I think it's a good idea.
Now, what did you say was the actual connection you think between something about the high frequency gives you some other power of something which makes something more detectable or something?
Yeah, in terms of generate, if you wanted to generate something in a lab and see a measurable effect, it's easier to generate high frequency gravitational waves than it is lower frequency gravitational waves. That's for the generation side.
What about during the detection? So I don't understand. It would seem that you have to understand what gravity is in order to build a detector of any kind of gravity wave.
Yeah.
And what was the connection you're trying to make there?
Yeah, for detection, the interesting thing about higher frequency gravity waves is you can measure them cosmologically too, or you can use it in a lab to measure, did your generator work? So I would like to have a generator and a detector that work together so I can use it in a lab to measure the response of materials. Then you have a gravitics lab, right?
Well, it still doesn't tell me that what you've detected is, gravity per se. You must be theorizing there is a connection between the high frequency gravity wave, which I could create by, I don't know, spinning an iron rod around, I suppose that would generate a higher frequency gravity wave. I suppose any kind of, electrical means of doing it, but that's kind of the way I'm thinking about it. Just take a ball of concrete and you spin it around as fast as you can. That should theoretically create a gravity wave. But from a theoretical standpoint, if you're talking about something electrical that's going to try and detect something like that, I still don't understand what is your connection, electrically.
Yeah,
because, you did mention this connection between electricity and gravity, and we all want to find that. And it's like, but you'd have to have already made that leap, right?
The connection is the gravity wave itself. You don't want it to electrically be connected. The detector should be detecting the gravity wave.
Now, Gary, do you want a moment, Gary, or because I can?
I could use a glass of water.
Yes. Let me. Yes, go for it, sir.
Okay.
Sorry about that.
Gary runs off. I have a question for Franklin, maybe to clarify. What Gary was saying is that if you take a wave, like a photon emission or a very high frequency electromagnetic potential, and you squeeze it by external fields so that it takes up a smaller volume of space, the energy in that volume of space is higher because you've effectively compressed it. So as a result of changing the physical geometry in which the energy takes place, you produce a change in the fundamental space-time metric that's there. You change the space-time curl vector because you're conducting that field through some volume through a medium of space. And
you're still talking about actually physically compressing something, just
right.
like they go, they're compressing the arms of like 2.3 meter, mile.
Plasma. You have a plasma that's traveling in one direction, and you squeeze that plasma down to a very small area, and it has, it's an ionized plasma, so its electric field is now in a smaller area, and it has a motion to it. So it's not just a uniform plasma, but it actually has a characteristic where it has areas of high concentration, low concentration in its energy. If you continuously compress and expand this plasma, it's going to have an effect on the medium that's carrying its electromagnetic functions, and that would be the space around it. So that's where you're going to get your emissions from, is from compressing the plasma and consequently increasing the volume of energy in a given space. Am I understanding that correctly, Gary? Because now you're back.
Yeah, so, right, you are. And actually, the important part about the third International High Frequency Gravity Wave Conference was I had a conversation with Andrew Beckwith on the tokamak approach. And he did the math and felt the only way it would work would be if you had a burning plasma. Because if you're resonating the plasma in a quadrupole way, just the plasma oscillation didn't have enough mass to trigger the level of gravitational response that we needed to see. It needed to be a burning plasma. So ideally, if you had burning nodes, if the plasma is bouncing back and forth in quadrature, and when it hits together, it burns, right? It creates fusion. And when it bangs back, it creates fusion. If you have those 4 burning nodes, then that's enough mass energy change to be able to break the threshold of detection.
Yeah, I would imagine that is the big deal in detection, because gravity is so small.
That's because the coupling is so small. And the other way to improve that, which Sir Fadi is pointing out, is can you change that coupling constant, that G over C to the 4th coupling constant, using a material that helps exaggerate or concentrate those gravitational lines of flux. Just as we use an iron core in a coil, can we use high permeability materials to strengthen that gravitational coupling? And the answer he predicted through his S matrix, his 0-rank tensor, looks like yes. Even in isotropic material with high permittivity or permeability, the answer seems to be yes. It seems to be more pronounced with permittivity. It goes to the 4th power of permittivity. It only goes to the squared power with permeability.
Well, then there wouldn't still seem to be a very good connection between electromagnetic, say, and gravity. I mean, actually, another reason why I tuned in onto this talk was that you said high frequency gravity. Now, basically, my own hypothesis is that gravity itself is actually a high frequency wave. Have you ever heard of that hypothesis? And,
very, very well may be. I mean, one of the Mach's principles is that inertia is springing from the superposition of all these gravitational effects, and that's what's causing inertial drag. So under that scenario, you could reduce inertial drag by creating a frequency cutoff if you can somehow shield certain higher frequency gravitational waves, you can shield yourself from inertia. So you might be onto something. I mean, I don't know the theory behind all that. Well,
it reminds me a little bit about Bob Lazare's theory, where he said there's this A gravity and there's that B gravity. Now, to me, that sounds an awful lot like the symmetry we get in charges, where there's a positive charge and there's a negative charge, right? Yeah. So essentially, there may in fact be a negative gravity.
Right, and Einstein's field theories don't really take that into account. It just takes it as a given that there's one gravitational coupling constant. There may be more than one flavor of gravity. And in fact, Heim theory says that there is. I have published on ResearchGate, on my ResearchGate, a review I did of Heim theory a couple of years ago in which he predicted 3 different flavors of gravity. So you may want to take a look at Heim theory too. There were a number of mathematical errors that were found in 2011 or so. So people kind of dropped looking at Heim theory, and it's also very convoluted. But he was a German physicist that was trying to work on a unified field theory. And in order to make it all fit together, he had to have 3 different types of gravity.
I would think that according to Blablalar, we'd expect to find 2 kinds of gravity, and he seemed to imply that the alien technology was such that you could actually create a gravity gun. I mean, I've kind of seen these on the cartoons where literally they have a gun that shoots a beam of gravity, and you can do things with it.
Yeah, I did present in the 3rd gravitational wave conference heterodyning 2 high frequency gravitational waves to get 1 low frequency one, and to see if we took 2 high frequency ones, heterodyne them together with a small frequency difference, could we create a signal strong enough for LIGO to measure? I think kind of the jury's out. It depends upon what kind of generators we're using. With burning plasma generators, it may be possible, but we would need at least very strong burning plasma tokamak generators to be able to pull it off. But that is also another way to create like a tractor beam or a gravity weapon, as it were, where if you take a very small frequency difference between 2 highly tuned high frequency gravity waves, and you're getting that small difference between, or superposition between the 2 of them, is there a way you can create a scalar effect there? And there may very well be.
Yes, there is.
Okay, sorry. Yeah, Mark had a question as well. So.
Oh
sorry.
yeah, I just wanted to comment on what Franklin was saying. First of all, my belief on Bob Lazar is that he saw real craft and he was fed a BS explanation as to how they operate. And one thing that was very telling about his presentations, especially the early ones, is that when he went into the base of the craft, he saw what he thought looked like microwave waveguides, and they told him they were gravity waveguides, and they're moving this gravity A wave and B wave and of an element 115 that turns into element 116, which is antimatter, which we all know is impossible. So I think the explanation that he was given is complete BS. It was meant to lead us in the wrong direction. But that insight that there was microwaves in the base of the craft, tuned tubes or tuned cavities in the base of the craft, really has something to do with how the craft operated, instead of being actual gravity waves. And that fits in more with the dynamic nuclear orientation aspect of how these craft can work with the Alciphon theory, which we'll get into later.
Okay. So I think we're just about there. Does anyone else have any more questions, or should we give?
Ron did, but he wasn't able to unmute.
Oh,
so you need to hover towards the bottom of the window, Ron, and look for the mute.
Unmute. You hear me now?
Yeah, I can hear you now.
Oh, good. Right. I'm very interested in your metamaterials.
All right.
Especially with the forward toroid. But
I think it would be a good combination. I think it'd be really interesting to look at the effects of that. And that's something that's driving me towards, why don't we get a gravitics lab that can start looking at some.
You need a gravitics lab.
I think so.
First of all, I mean, I would go back right to linearized gravity. What you first of all need to do is to be able to generate gravitomagnetism in your gravitomagnetic lab.
Once you have that, then you have a source of a signal that you can use to see the effects of other materials, but you need that link first, that generator and detector, before you have a lab.
Right. Let me just throw something in. You've heard of Faraday rotation?
Yes.
Right. I think that may be the way to do it.
Well, some of the sightings have said that they've observed Faraday rotation. So very interesting. I mean, it's very.
No, I don't mean. I mean, the Faraday rotation with a changing. Well, normally it would be with a magnetic field, Does Faraday rotation work with gravitomagnetic field?
Yeah.
In which case, we might be
as
able
a detection. You're saying as a detection mechanism.
As a detection mechanism, which we haven't done yet.
No. I haven't looked at that, actually. That's a good idea.
Yes. And I think we might find in a laboratory on Earth, we can create gravitomagnetism and detect it, which nobody has realized. Well, we looked at the Earth rotating and its gravitomagnetic field, and the gravitomagnetic permeability of space is virtually zero. But inside materials, as you said.
Materials, exactly.
Yeah.
If you do this inside materials, it will have a whole different effect.
Yes.
As that S matrix just pointed out, right? This is what Jack's been on about.
That's what we want, a metamaterial for gravitomagnetism, not for magnetism.
Right. It'll be a different design. Yeah.
It'll be a different design. Yeah. Well, the US has got the money. UK's got no money.
We're not spending it in the right places.
Okay. Right.
All right.
Thank you,
Tim.
Tim.
To prop up the stock market.
Well, Gary, we would personally like to be your go-to gravity lab.
Fabulous. I'm glad someone's
do that for you.
Actually, we've had early on, we had an intern, Adam Keegan, who actually worked on LIGO. He was in charge. Yeah, he was in charge of the interferometer setup.
Yeah.
The one thing that people don't realize about LIGO is that it's not just one observatory. There's several observatories around the world, and the equipment is so sensitive. They're measuring car crashes 10 miles away, or trucks driving over a bridge or something like that. They're extremely sensitive.
Multiple. Yeah, you need one in Hanford. You need one in Livingston. Yeah.
Yeah, you need one all over the world. One in Germany. That's why his professor actually had to split the Nobel Prize over it, because the only way they could really say that this came from out of the planet was because they got the same impulse in Germany and here in America at the same time. So
Virgo.
Yeah, these gravity wave detectors that they're dealing with, the laser interferometer system, they're very, very sensitive to noise, and it's not really applicable to a lab. But what you're talking about is something that's literally tabletop.
Yeah, exactly. Yeah.
And as long as we can figure out how to get that 9 Tesla field without blowing everything up, I think this is something we can do here in the lab. We have enough wire, we have enough current. Hybrid battery systems can definitely provide that much power.
Up to 200, 300 kilowatts.
Yeah. I mean, I can combine it. I have several tons of nickel metal hydride batteries in storage. We can charge them all up, and any amount of current you want is available here at the Falcon Space Lab.
That's great.
And if you want to fly down here to help us out with it, all expenses paid. It's already taken care of.
I would love to have a look sometime.
Okay, well, I think we're just about done. So again, let me unmute everybody, and we will give Gary an enormous applause. Sir, thank you so much. Thank you so much. So let me invite everyone to unmute, and again, an enormous applause for Gary. Okay.
Nice. That was amazing.
Woo!